Hi. So endogeneity is or can be a very daunting task, especially when you want to publish in a journal and then the reviewer tells you, well, you have to address endogeneity. That's why, together with my colleagues at the University of Zurich, we built the package REndo, which addresses endogeneity without the need of external instrumental variables. But I mentioned already 3 times the word endogeneity, but what is it, endogeneity? It's just a very fancy word for a very simple problem. Basically, you have a regressor, or one or more, like here P, which is correlated with the error epsilon. When this happens, you have a problem of endogeneity. Why do you care about it? Because this will render your coefficient estimate, beta 1, biased and inefficient. Moreover, if your endogenous variable P is correlated with X, this will also create a problem with beta 2. The estimate of beta 2 will as well be biased. The most forms of endogeneity appear when you have an omitted variable in your equation, which is correlated with a dependent variable. When you have a measurement error, when one or more of your regressors are measured with error, or when you have simultaneity, like in the case of supply and demand or sales and advertisement sales. How do you cure endogeneity when you have secondary data? Is either with instrumental variables, with matching methods, or with regression discontinuity. These are the most used. So here is where REndo comes into play. Instrumental variable, most of you would think, well, you have to have an external instrumental variable, right? That you have to find an additional variable that is correlated with the endogenous variable, but it's not correlated with the errors. It doesn't impact the dependent variable directly. So it's a lot of assumptions. But there exist also statistical approaches which are called internal instrumental variable methods that were encoded now in REndo and that will bring you to you. So REndo actually brings 5 of these internal instrumental methods, which I will present each of them in the next slides. So consider you have a model where P is your endogenous variable, meaning that it's correlated with your error. And then you assume that P is actually it's composed of Z and an error mu. So for internal instrumental variable, impose many assumptions on the Z. Z can be observed or unobserved, and in order for beta 1 to be identified, we need to impose assumptions on Z, where most of the time mu is assumed normal, but we'll go through it. So one of the first instrumental variable in a REndo package is the latent instrumental variable proposed by Peter Ebbes and his co-authors in 2005. The approach lets you have one endogenous variable and only one exogenous variable. And I have to tell you that in all the methods included at the moment in REndo, the dependent variable has to be continuous. So it doesn't address when the problematic when the dependent variable y is 0 or 1, right? Another assumption of the latent instrumental variable is that the endogenous variable shouldn't be normally distributed. Moreover, the Z is a discrete latent instrument with at least 2 groups with different means. And the estimation is done to maximum likelihood. Because of that, the function in REndo is called latent AV, where it lets the user give starting parameters. But if you have an intuition or you have an assumption, you can put them. If not, this will be taken as the coefficient of OLS running y on P. So this is the output of the function. I'm not sure you can see very well. So it returns, moreover, it returns some, oh, I'm sorry. I was wanting to point out. Where do I go? I'm sorry. Okay, so here. It returns P1 and P2 are the means of the assumed 2 groups of the Z, of the latent variable that P is assumed to be built with, and the sigma matrix. Moreover, it returns the Akaike and Bayesian information criterion and the starting parameters that were assumed by the model. The next model in REndo, it's called Copula Correction, which was proposed by Park and Gupta in 2012. And it's my personal favorite. It doesn't come with too many assumptions. You can have either continuous or a discrete endogenous regressor. You can have one or more endogenous regressors. It's estimated in the case of one continuous regressor with maximum likelihood. Otherwise, it's estimated with two-stage least squares. The only assumption is that your endogenous variable is not normally distributed, because the errors are assumed normally distributed. So then it cannot be identified, right? The call of the function is Copula Correction, and now depends. If you have one continuous endogenous regressor, you have to specify. You have here continuous P, and then if you have one continuous endogenous regressor, this will be estimated with maximum likelihood. And you have the option to give the starting parameters. Also, you have to specify the number of bootstraps, because some additional parameters are estimated, and that's why you cannot trust the standard errors. So you have to use the bootstrap standard errors. By default, it's 1,000 bootstraps, but will take quite a long time to run. Then in the second case, when you have two endogenous regressors, it's either two discrete or one discrete and one continuous, then the estimation, it's done with, actually we use IVReg from the AER package to do that. And what is nice in the case of one continuous endogenous regressors is that this, basically the Copula method models the correlation between P and the error with Gaussian copulas. And here what the output returns, here rho, it tells you what is the assumed correlation between the endogenous regressor and the error. And rho, here we see it's positive, it gives you the sign of this correlation. And the significance of P tells you if you have an endogeneity problem or not. So if P it's statistically significant, then that means that actually you have an endogeneity problem. Here it's in the case of more than two endogenous regressor, either discrete or continuous, where the method will use the empirical distribution function of the endogenous regressor and use that information to create an additional regressor in your model and add it in your IVReg function, and will spit out, for example, here to P star, to additional regressor, which the sign, if it's positive, tells you have the correlation between error and endogenous regressor, it's positive. And if it's statistically significant, it tells you that indeed you have an endogeneity problem on a P1 and P2 respectively. Now, a third method proposed by Leubel in 1997 is the higher moments method, which in REndo allows only for one endogenous regressor. And again, exactly what Leubel was saying, that the skewer, the better your endogenous regressor. And it relies on third moments of the data. That's why the efficiency of this estimator, well, it's not so, I mean, it's a problematic, but nonetheless, it helps you in maybe when you really don't have any other alternative, right? And here, what is nice that you can, how you call the function in REndo, it's higher moments IV, where in the first you specify the formula, then which is your endogenous regressor, then you have an IIV, which has an IIV part, which is the internal instrument to be computed. I'll explain in a minute, and the G function, the transformation to the exogenous regressor. So basically, the internal instruments can be have different formulas. You can multiply the dependent variable with the endogenous regressor, or you can have the endogenous regressor multiply with one of the exogenous regressors, and then G tells you which transformation should you use for the exogenous regressor. I'll give you, I mean, it sounds complicated, but we have a vignette, the package is already in CRAN, you have a help file, and then it's better explained maybe. For example, here, you create an internal instrument which takes the product between G and the P. P is the endogenous regressor, where G it's an x squared of which of the regressor x1 and x2. So basically, you can create here in this case, in second case, you create two internal instruments. One is the x1 squared multiplied by p, and second is x2 squared multiplied by p. And these are your instruments. And what is nice is like you can use, in this third example here, you can have, on top of this, you can create another internal instrument, which is just the product between the dependent variable and the exogenous variable. Here, we make use, we use IVReg, and then you have a diagnostic test, which is nice that it tells you whether your instruments are weak or not, in this case not. Yeah, the p-value is 0, so the null hypothesis of weak instruments is rejected. And then you have the Wu-Hausmann test, who tells you that indeed you have an endogeneity problem. Another method is the Heteroskedastic Errors, also by Leubel, proposed in 2012, which allows to have multiple endogenous regressors and is based on the heteroskedasticity of the errors. And what is nice that it has many assumptions, but one of which is very important, is that the covariance between the set of instruments and the square of the errors, it's different from 0, where Z in this case can be all of your exogenous variables or a part of it. So it can be x1 or x1, x2 in this case. I'm sorry, I'm terrible with this. Here in R, in REndo, you call the function head errors IV, when you have to specify which is your endogenous variable, and then in IIV, from which variables should be considered when you build the internal instruments. Moreover, if you have an additional external instrument can also be put. In this case, W, it's an external instrument. What is nice that in this case, if you have an external instrument, you can still build this with heteroskedastic error, with het errors IV, you can build external instruments and can improve the efficiency of your models. Here is exactly what I said, the same. You also have the diagnostic tests that tells you also if the instruments are weak and if you have an endogeneity problem or not. And the last model in REndo, it's the multilevel GMM method proposed by Kim and Fries in 2007 in Psychometrica. And what is nice that here you have multilevel models are, for example, imagine you have children embedded in classes embedded in schools, right? And the idea of the method is that we address endogeneity when the regressors are correlated with errors at a higher level. So for example, if you have a level 1 variable correlated with level 1 error, it's not dealt with in multilevel GMM. So multilevel GMM deals only when the level 1 endogenous variable is correlated with level 2 error or level 3 errors. And what is nice that this method outputs, compares the random effects model with fixed effects model and with GMM model at different levels. And then it tells you with an omitted variable test which one should you select. And why it's REndo relevant? Because it lets you address endogeneity without the need of external instruments, because it addresses endogeneity both in single and multi-level models, increases efficiency by including in your model these internal instruments, deals both with continuous and discrete endogenous regressor, and at the moment, it's the only package on CRAN that addresses internal instruments methods. Thank you.
Any questions?
I guess everybody's hungry.
Maybe. I have a quick one. So you mentioned in some of the previous models, the dependent variables can't be a categorical variable. What about the independent variables?
The independent variable can be of any form, can be continuous or categorical or discrete, so it's not a problem. Only the dependent variable at the moment, we didn't implement a model that deals with internal instruments but has as dependent variable non-continuous variable.
Okay.
But it's on the to-do list.